Alright, hello AP Physics students, and welcome to this video lecture, which is going to be going through how we can actually apply Newton's first law, Fig Newton's first law, to actual real-world scenarios. Before we get into that, though, I want to make sure that we're on the same page in terms of how we record forces, and namely that the units of force are these things called newtons, and we just abbreviate those with an N. Now, a newton actually stands for a kilogram meter per second squared, and I'm not going to get into this right now. That's going to make more sense as we move on through this unit on forces. However, I just want to present that to you so it's not goofy looking in the future. Now, one other thing that I want us to be sure that we're on the same page with is that forces are vector quantities. Forces are vector quantities. Because not only do we depend on the size of the force, we want to know how much force is actually there, but we also want to know which direction that force is acting. Okay, so those are the two big things that I want us to be on the same page with before we get into how we can actually apply Fig Newton's first law. So when we actually think about Newton's first law, we know that we have balanced forces, and we know that objects are going to want to keep doing what they're already doing because of those balanced forces. And we can call those situations where objects want to keep doing what they're already doing because of those balanced forces, we can call those equilibrium situations. We can get even fancier, and we can call this static equilibrium. So static equilibrium situations just mean that we have those balanced forces, and we can analyze those forces because we know that there is no external unbalanced force acting on whatever object we're dealing with. Okay, now to analyze these static equilibrium problems, what we have is we have these things called equilibrium equations, where we say that the sum of all forces is equal to 0. What this means is that the sum of all forces is equal to 0. That means that we have balanced forces. Okay, now this is a pretty general equation here. We can actually break this equilibrium equation up a little bit more, and we can talk about the different directions that we have acting on that object. Now, I want you to think back to 2D motion. We had motion in the x and the y direction. Just like in dynamics, we can have forces in the x direction, and we can have forces in the y direction. Okay, so in these static equilibrium problems, in these equilibrium situations, we know that our forces in the x direction are going to equal 0 because they are balanced in the x direction, and we know that forces in the y direction are going to equal 0 because they are balanced in the y direction. Okay, so application of Newton's first law, we can analyze equilibrium situations or static equilibrium problems. We know that forces are balanced, therefore all the forces on that object are going to sum to 0. And this equilibrium equation can be broken down into the two different directions that forces can act. Okay, so the next couple slides are going to go through actual problems demonstrating how we use these equilibrium equations, so please follow along carefully. we'd have our XY axes labeled like this, okay? Well, we can actually tilt those for this scenario. So we can say that X is going this way and Y is going this way. And then I'm just going to get rid of these axes that I had here. Okay, so now in our X direction, what do we have? Well, we have our force due to friction, which we're going to say is going in the positive direction. And now notice that we actually have to split our force due to gravity up into its X and Y components. Okay, so we're going to have here then FGY, and then we're going to have FGX. And this angle right here is the same angle of our hill, which is going to be 30 degrees. Okay, so completing my equilibrium equation in the X direction, I have minus FGX. Okay, so that is taking care of my equilibrium equation in the X direction. Now we can extend this out and actually solve for our force due to tension. Okay, so we're going to have Ft minus 77, because that was our weight of our sled, and this is going to be times the sine of 30 degrees, and we know that this is equal to 0, and I forgot to put that here too. Okay, so we know this is equal to 0. So if we solve then for our tensional force, we are going to get Ft is equal to 38.5 newtons. Okay, so there is the force exerted on the rope by the child. That's our force due to tension. There we go, 38.5 newtons. Now, I'm going to get rid of this stuff here. No, not all of that. Well, let's just do this. There we go. I'll shrink that up a little bit. Now we can work in the Y direction. Okay, so I'm going to have summation of forces in the Y is equal to 0. And what do we have in our Y? Well, we have our normal force, and then we have gravity in our new Y direction. Remember, because we tilted our axes. So now we have minus FGY. And again, we're going to extend this out. So I'm going to have Fn minus 77 cosine now of 30. And that's all going to be equal to 0. Again, I forgot to put that up here. Okay, and then we just solve. So we're going to get Fn, or our normal force, or the force exerted on the sled by the hill, is going to be equal to 66.7 newtons. Okay, so there's an example of how we can use these equilibrium equations to then solve for unknown forces acting on an object. And this is a very unique scenario because now we are working with an object sitting at some angle. We are no longer just horizontal, we had some angle here. But a very useful tool that we had here is we can actually tilt that axis to simplify this problem down a little bit. Now you could very well keep the XY axes like this, okay? It's not something that you have to do. However, I think in this problem it simplifies that down because we had two forces, one perpendicular and one parallel, with these new axes, okay? So one more problem coming at you here. All right, this next problem, we have a traffic light weighing 100 newtons hanging from a vertical cable right here, and it's tied to two other cables right here and right here. And those two other cables make angles of 37 degrees and 53 degrees with the horizontal. So you can see that in this picture here. So we actually need to find the tension in each of the three cables. Now, for this problem, there's one there's one of the tensions in the cable that we can really easily find right away, and that's T3 here. Okay, notice that we're going to have gravity acting down in this problem, and this tension acts straight up, so we can find T3 right away. So let's draw a free body diagram for T3. So we're going to have T3 going straight up. We have force of gravity going down. So we can write our equilibrium equation for this free body diagram, and we're going to have T3 minus Fg is equal to 0. Okay, and then we can just plug in what we know. So we don't know T3, however we do know that our light weighs 100 newtons, and that's equal to 0. Rearranging that, we get T3 is equal to 100 newtons. Okay, so that's one of our things, or one of our tensions figured out really quickly. Now the next two are going to prove a little bit more challenging. So I am going to get rid of this stuff so we have some room to work. And I'm going to draw another free body diagram here now. And what this free body diagram is going to actually be taking a look at this point right here. So we're going to be having T3, and then we're going to have, let's do T2 like this. That's T2, and then we have T1. Wow, that's a really not straight line. Okay, and there's T1. So we know T1 is at 37 degrees, and then we know T2 is at 53 degrees. Okay, so there's our situation. Now we need to create equilibrium equations in both directions. So our summation of forces in the y direction, we'll just start out with the y, it doesn't really matter. And let's say first off we have T1, we have T1, and in the y direction that's going to be sine of 37, and then we have plus T2 sine of 37, and then this is going to be minus T3. Well, we know that T3 is equal to 100, but we'll just leave it like that for right now. Okay, and then now in our x direction, summation of forces in our x direction, we are going to have, and I'm going to write negative T1 cosine of 37 plus T2 cosine of 53. And I just noticed that I wrote 37 up here for T2. That's not right. 53. Okay, and this is equal to 0. Now, we have two unknowns, and fortunately we have two equations. So if we have two unknowns and we have two equations, we can solve for both unknowns. So what I would encourage us to do here is first we're going to use our summation of forces equation, or our equilibrium equation in the x direction, to find an expression for one of those two forces. So let's find an expression for T2. Now I don't want to insult your intelligence finding the expression, so I'm just going to do this here. If we rearrange our force equation, or our equilibrium equation in the x direction, we're going to get T2 is equal to 1.33 T1. Okay, so that's what we're going to get there. We're going to get T2 is equal to 1.33 T1. Now we can actually substitute that into this equilibrium equation in our y direction. So let's do that here. I'm going to make this, actually let's just scoot that up a little bit. And then can we make it smaller? Oh boy, doesn't like me. Okay, so let's substitute, there we go. Well, let's substitute T2 into our equilibrium equation in the y direction. So we're going to have summation of forces in the y equal to 0, and that's going to be equal to T1 sine of 37. And now we're going to have, let's see, this is going to be plus 1.33 T1 sine of 53. And then we're going to be subtracting the 100 newtons because we know what T3 is. And then this is all going to be equal to 0. So if we simplify this down, I'm not going to go through all the steps, but we're going to get T1. We're going to get T1 is equal to 60.1 newtons. And now, knowing T1, we can just substitute that back into this expression right here to then get a value for T2 of 79.9 newtons. Okay, so our answers then for this problem, T1 is equal to 60.1 newtons, T2 is equal to 79.9 newtons, and then we also found T3 was equal to 100 newtons. Okay, so I apologize that this video lecture was a little more lengthy. However, this is kind of our first experience with actually applying Fig Newton's first law. So I hope that this video was helpful and gave you some insight as to how we solve these problems using our equilibrium equations. And take care, AP Physics students.